the invisible shield that protects us. Imagine an Earth without a magnetic field, without protection from the solar wind, without a compass, without stable navigation. What if one day it disappeared or started behaving unpredictably? Every year, scientists record anomalies more and more often. The South Atlantic anomaly is expanding. The northern magnetic pole is rapidly drifting towards Siberia, and the field strength is decreasing. What is this, the beginning of a geomagnetic inversion or something completely new? The Earth's magnetic field is one of the most mysterious and important components of our planet. It is invisible, but vital. In this video, we take a fascinating journey deep into the Earth's core to understand. How is the Earth's magnetic field formed? Why is it weakening, and what is the South Atlantic anomaly? Is a pole shift possible in the near future? What will happen to mankind if the magnetic field disappears? Fasten your seat belts. We begin our dive into the deepest and most mysterious processes that shape our world. How does the Earth's magnetic field work? The magnetic field is created by geodynamo, the movement of molten iron in the Earth's outer core. These movements create electric currents, and the currents in turn generate a magnetic field. It extends far beyond the planet, forming the so-called magnetosphere, an invisible cocoon that protects us from the solar wind and cosmic radiation. Interestingly, the magnetic field is constantly fluctuating. It strengthens and weakens, changes shape, and even flips over. Scientific data confirms that magnetic inversions have already occurred in the Earth's history, when the North and South poles changed places. What is happening to the field today? Over the last 200 years, the strength of the magnetic field has decreased by about 9%. That's not just a statistic, it's a troubling symptom. Scientists are particularly concerned about the South Atlantic anomaly, an area over South America and the South Atlantic where the magnetic field is particularly weakened. It is in this region that satellites fell more often and the radiation impact on them increases. Some scientists believe this is a sign of an inversion that has begun. Others say it's a temporary anomaly. But a growing body of evidence suggests the magnetic field is behaving erratically, and the consequences could be serious. The poles are on the move. The magnetic North Pole, which was still in Canada at the beginning of the 20th century, is now rapidly moving towards Siberia. Its speed has more than tripled from 15 km or year to 50-60 km or year. Scientists from the U.S. Geological Survey and the Alvin Institute of Geophysics are watching this process with alarm. Such a shift could affect navigation systems, aviation, satellites, animal migrations, and even climate. And if the inversion really begins, we will be witnessing a grand but dangerous phenomenon. New alarming signals. The Earth's magnetic field, which for billions of years has protected life from cosmic aggression, is now beginning to behave strangely. Scientists from around the world are watching this process with alarm. Back in 2020, satellites of the European Space Agency's Swarm mission recorded serious deviations in the structure of the field. A particularly mysterious zone is the South Atlantic anomaly. Here, the magnetic field is weakened so much that spacecraft literally sag in their defense. Some of them even fail because of the increased flow of radiation. It's been called the Earth's weak spot. But what is even more surprising within this anomaly began to form a second point of minimum. That is, the area where the field practically disappears. This could be a sign that a geomagnetic inversion is not just possible, but has already begun. Pole drift, an acceleration not expected. The North Magnetic Pole is leaving Canada and rushing towards Siberia at a speed of up to 60 kilometers per year. For comparison, at the beginning of the exact century, its speed was only 15 kilometers per year. This process has accelerated so much that international services had to urgently update navigation maps and programs. But why is this happening? The magnetic field is created deep underground in the outer core, where liquid iron and nickel form giant currents. When those currents change, the magnetic field changes. And since we cannot look there directly, all that we see, this is only the surface manifestations of much deeper and still incomprehensible processes. The pole shift is already affecting aviation, navigation, and even the migration routes of animals. Some species of birds and sea creatures are losing their orientation. This may seem like a small thing, but at the level of the biosphere, it is a wake-up call. What if the magnetic field disappears? The complete disappearance of the Earth's magnetic field is a rare but theoretically possible scenario. Although in practice, it would likely just weaken greatly, the consequences of even a temporary disappearance would be catastrophic. Let's imagine there is no longer any magnetic shielding on the Earth's surface. What's in store for us? Radiation shock. Solar wind and cosmic radiation reach the surface unhindered. Ordinary magnetic storms become deadly. This leads to an increase in cancer, mutations in DNA, massive reproductive failures in animals and humans, collapse of satellite systems, navigation, meteorology, internet, military systems all operate through satellites. In the absence of a field, electronics overheat, atmospheric ionization increases, and satellites fail one by one. Power problems. Magnetic storms are already capable of causing power grid failures. If there is a strong inversion or the field weakens by a few percent, the consequences could include nationwide power outages, transformers failing, communications and internet outages, climate fluctuations. Although a direct link between the field and climate has not yet been proven, there is evidence that dramatic changes in temperature patterns and air mass circulation have occurred during past inversions. Psychophysiological impact. Some scientists and alternative researchers claim that the magnetic field affects brain rhythms, biorhythms, mood, and even time perception. When the field is weakened, anxiety, sleep disorders, and depression can increase. It's happened before. The history of geomagnetic inversions. Magnetic field inversions are not science fiction. They are a documented geophysical fact. Over the past 20 million years, the Earth's polarity has reversed more than 80 times. The last major inversion, the Bruns-Matsuyama inversion, occurred about 780,000 years ago. Then the north and south magnetic poles literally switched places. The transition took several thousand years. But there were also faster, shorter-term events, geomagnetic excursions. For example, the Lecampa event about 41,000 years ago lasted only a few hundred years. The field intensity dropped to almost 5% of normal. What's interesting, this event coincides with a number of climate anomalies and the extinction of some species. Some scientists even believe that this is when Neanderthals began to disappear, giving way to Homo sapiens. Humanity survived. But back then, it was not technologically dependent on power grids and satellites. Today, the situation is quite different. Magnetic field and technology on the verge of failure. Modern civilization means thousands of satellites, millions of kilometers of cables, sophisticated navigation and communication systems. All of this is vulnerable. Even a slight weakening of the magnetic field can cause massive GPS failures, especially in aviation and military applications, affect cell phones and the internet, increase errors in navigators in cars, airplanes, ships, disrupt financial systems and bank servers, endanger astronauts and manned missions into space. Polar regions, where the magnetic field is already weaker, are especially sensitive to these phenomena. It is there that disruptions in satellite communications and failures in electronics are already being recorded. Despite all the warning signs, mankind is already thinking about defense. Scientists, engineers, and international agencies are developing scenarios to adapt to a possible inversion or weakening of the magnetic field. Infrastructure protection. Magnetic shields on satellites. Many satellites are already being equipped with additional radiation shielding. In the future, if the field weakens, such measures will become mandatory. The development of special miniature magnetic fields around satellites is possible. Redirecting satellite orbits. If it is known that the magnetic field is weaker in a particular area, for example, the South Atlantic anomaly, satellites can be reorbited in advance, either temporarily or permanently. Underground storage and backup systems. Underground data centers, shielded from external radiation, are being established to protect critical information, especially government data. Medical adaptation. Magnetically shielded chambers. These technologies can be used in space, in underground laboratories, and in medical centers. The chambers shield against radiation and maintain a stable magnetic environment, which helps reduce stress and physiologic strain. Anti-radiation drugs. Scientists are working on substances that increase the body's resistance to ionizing radiation. This research is funded, among other things, in preparation for future space missions. Scientific monitoring and response. Monitoring networks. Worldwide agencies such as ESA, NASA, and university laboratories monitor geomagnetic activity 24 hours a day, 7 days a week. Rapid warning centers for storms and anomalies are established. Response protocols. Guidelines are being developed for energy companies, airlines, military, and rescue services. In the event of a magnetic anomaly, risks can be mitigated in advance. Shut down sensitive equipment, change routes, limit activities in dangerous regions. Magnetic field and biosphere. We're used to thinking of the magnetic field as something technical, but in fact, it affects the entire biosphere, including animals and possibly even humans. Animal migrations. Many species are oriented by the magnetic field. Birds, geese, pigeons, storks, sea turtles, salmon, bees, even bacteria. They have special cells or molecules in their bodies that are sensitive to the magnetic field. If it changes, animals can go off course, fail to find a breeding ground, or die along the way. Geomagnetic sensitivity in humans. So far, this question is controversial, but some scientists suggest that humans also sense the magnetic field subconsciously. There are hypotheses that changes in the geomagnetic environment can cause headaches and anxiety, sleep disturbances, decreased concentration, spikes in aggression or depression in years of increased solar activity. Heart attacks and traffic accidents are reported to increase. Does the magnetic field affect the climate? Official science has yet to give a direct link between geomagnetic changes and climate change. However, interesting correlations are emerging. During the Lecampa event 41,000 years ago, there were climate anomalies, cooling, and mass extinctions. As the field weakens, the inflow of cosmic radiation increases, which can change cloud cover and hence temperature. The magnetosphere is involved in protecting the atmosphere from ionization, affecting the processes on which the circulation of air and water depends. It is also worth noting that the magnetic field can interact with solar activity, and that, in turn, affects climatic processes on Earth. So far, these are just hypotheses, but more and more scientists are paying attention to them. Alternative hypotheses and mysteries. When it comes to magnetic fields, there are not only scientific theories, but also hypotheses that go beyond academic science. Magnetic field as a carrier of information. Some researchers believe that the field can preserve the fingerprints of evolution. That is, it is not just a protection, but a kind of energy memory of the planet. This idea sounds almost mystical, but finds support in theories about the holographic nature of the universe. Field and consciousness. Supporters of this idea claim, during strong geomagnetic storms, people have more vivid dreams, intuition increases, and unusual states of consciousness arise. There are even studies linking the level of geomagnetic activity with mass moods in society. Cosmic cycles. Some scientists hypothesize that changes in the magnetic field are due to the solar system passing through different parts of the galaxy. For example, through spiral arms where there is a higher density of stars and radiation. This may explain regular geomagnetic inversions and climate crises on the planet. Esoteric versions. In esotericism, there is the notion that the magnetic field restrains higher forms of energy, and its weakening would open a window of opportunity for a new era of consciousness. Such ideas are popular in spiritual circles and futurological theories. The magnetic field is not just a physical phenomenon. It is an invisible shell that has protected life on Earth for centuries. It's a cosmic barrier keeping chaos out of the atmosphere, but today, that shield is faltering. We are witnessing its instability. Perhaps an inversion is coming. Perhaps it's just a temporary anomaly. Science has yet to provide definitive answers. But one thing is certain: all life on this planet depends on this delicate, fragile structure. And the further we advance in technology, the more we realize we're vulnerable to it. Doesn't matter how powerful our computers and rockets become if the magnetic field disappears. The basis for stability disappears. But there is another side to this. We have the brains, the knowledge, and the combined science to not just predict, but to act. We have a chance to not just survive, to adapt and become stronger. Today, we stand on the brink of change. We face not only a challenge, but also an opportunity to better understand how the Earth works, and maybe the whole universe. If you are close to science, if you feel at the greatness of the planet, if you want to know what will happen next, stay with us. There are more mysteries to come. And perhaps the most important discoveries are yet to come. the invisible skeleton of the cosmos. Close your eyes and imagine the night sky. Countless stars, galaxies swirling like celestial whirlpools, infinite darkness in between. But what if that darkness isn't empty? What if the vast majority of our universe is made of something we can't see, can't touch, and barely understand? Welcome to the enigma of dark matter, an invisible substance that outweighs everything we can see, yet leaves no light behind. It's not just a mystery, it's the scaffolding of reality itself. Without dark matter, galaxies would fall apart. Stars wouldn't form. Life as we know it might never have existed. In this video, we'll plunge into one of the most perplexing questions in physics. What is dark matter, and how does it shape the cosmos? From the earliest moments after the Big Bang to the invisible web connecting galaxies today, dark matter holds the key to understanding not only space, but our place within it. A shadow revealed by gravity. We can't see dark matter, but we can feel its pull. In the 1930s, astronomer Fritz Zwicky noticed something strange. Galaxies and clusters were moving too fast, as if held together by an invisible hand. He coined the term dark matter to describe the unseen mass that must be there. Decades later, Vera Rubin confirmed this behavior within spiral galaxies. Stars orbiting the galactic center move too quickly to be explained by visible mass alone. Something hidden and massive was stabilizing them. This wasn't just a small anomaly. It was universal. Dark matter, it seemed, made up most of the universe's mass. What dark matter is not. Before we define what dark matter is, we must first understand what it isn't. It's not stars, not planets, not dust, not black holes at least, not ordinary ones. None of the familiar matter known as baryonic matter can account for the strange gravitational effects. It doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic forces. In fact, the only way we know it's there is through gravity. Whatever dark matter is, it lies beyond the standard model of particle physics. It's a ghost in our equations present, powerful but invisible. The great search for the invisible. Scientists around the world are on a mission to uncover dark matter's identity. They've proposed candidates like WIMP's weakly interacting massive particles, Axion's ultralight particles predicted by string theory, sterile neutrinos, ghostly cousins of the neutrino, massive underground detectors like Xenot in Italy or Lux Zeppelin in the US wait silently, hoping to catch a rare collision between dark matter and ordinary atoms. Space telescopes scan the heavens for signs of annihilation, decay, or gravitational lensing that could reveal its nature. So far, no confirmed hits, but every silence narrows the search. The cosmic web. Dark matter doesn't just exist, it structures the universe. Computer simulations, like the Millennium simulation, show that dark matter formed vast filaments stretching across the cosmos, the so-called cosmic web. Galaxies form where these filaments intersect. Superclusters and voids trace its skeleton. Without dark matter, the universe would look nothing like it does. It is the architect of the cosmos. This invisible network binds galaxies together and creates the framework upon which visible matter accumulates. Dark matter and the Big Bang. To understand dark matter, we must return to the beginning. Just after the Big Bang, the universe was hot, dense, and chaotic. As it expanded and cooled, tiny fluctuations in density appeared. These were amplified by dark matter which, unlike regular matter, doesn't interact with radiation and cooled faster. It clumped early, forming gravitational wells that later drew in ordinary matter. In this way, dark matter seeded the structure of galaxies and clusters long before stars were born. The oldest light in the universe, the cosmic microwave background, even shows hints of dark matter's fingerprints in the temperature fluctuations. Alternative theories and bold ideas. Some physicists ask, what if there is no dark matter at all? Alternative theories like modified Newtonian dynamics or emergent gravity attempt to explain the galaxy rotation problem by modifying the laws of gravity at large scales. Others look to extra dimensions, supersymmetry, or even entropic forces as explanations. Still, dark matter remains the leading theory not only for galaxies, but for the cosmic web, lensing effects, and early universe evolution. But the fact we haven't detected it directly, that keeps the debate alive. What if we finally find it? Imagine we detect dark matter tomorrow. What would that mean? It would revolutionize physics, proving there's a hidden layer to reality, a new class of particles, a new force, or even a mirror universe. It could also open doors to futuristic technologies, dark matter engines, gravity manipulation, even novel energy sources. And philosophically, it would remind us that the universe is still full of mystery and that the visible world is just a fraction of what truly exists. Shadows that shape reality. Dark matter is like wind, invisible but powerful. It sculpts galaxies, binds clusters, and holds the cosmos together. We may not see it, but it is everywhere. In the next decades, we may finally unveil its true nature. Until then, we chase shadows and find the shape of reality in the darkness. Stay curious, explorers. The universe has only just begun to reveal its secrets.
In the 1960s, the world watched an exciting space race between the two superpowers, the United States and the USSR. The height of the Cold War motivated each of these countries to prove their leadership and technological superiority. The Soviet Union reached a milestone by launching the first man into space, Yuri Gagarin, which forced the US to urgently step up its efforts and set itself an even more ambitious goal: sending a man to the moon. For America, this was not only a matter of prestige, but also a chance to show the world its scientific and technical capabilities. To achieve this goal, NASA created the Apollo program, one of the most complex and expensive programs in the history of space exploration. The goal was ambitious, and the path to achieving it was far from easy. The first launches were fraught with difficulties. In 1967, tragedy struck a fire broke out aboard the Apollo 1 spacecraft, killing 3 astronauts. This incident was a lesson for NASA and led to the revision of many safety protocols and technological approaches. Afterward, NASA stepped up training and conducted numerous tests to avoid similar mistakes in the future. The Apollo 11 mission was the pinnacle of the entire program's efforts. The team consisted of Neil Armstrong, Buzz Aldrin, and Michael Collins. Armstrong, the mission commander, was to be the first man to set foot on the moon. Aldrin was to join him, and Collins remained in orbit in the command module, maintaining communications and ensuring safe return. The crew went through rigorous training, simulating possible problems and critical situations they might encounter on the moon. On July 16, 1969, a Saturn V rocket designed specifically for the Apollo program launched from Cape Canaveral Space Center. The crew set course for the moon, and their 4-day journey to Earth's satellite began. This flight was filled with both technical challenges and tense moments. The astronauts were at a great distance from Earth, and any malfunction could jeopardize the entire mission. When the crew reached the moon's orbit, another important part of the mission was completed. On July 20, 1969, the risky step began, landing on the surface of the moon. Armstrong and Aldrin transferred to the Eagle lunar module and began their descent. But they soon realized that the automation had led them to an unfortunate landing spot with rocks and slopes dangerous to the lunar module. Armstrong made the decision to take control and discreetly, but quickly, steered the module to a safer location. This moment is remembered by many as the culmination of the pilot's bravery and skill. A few hours after landing came the moment that changed history forever. Neil Armstrong opened the hatch of the lunar module and took the first step onto the surface of the moon, uttering his famous words, "It's a small step for man, but a huge leap for all mankind." He was soon joined by Buzz Aldrin, and the 2 astronauts spent about 2.5 hours on the lunar surface. They collected lunar soil samples, planted a US flag, and left commemorative plates. This moment came to symbolize the unifying power of science and technological progress. After the successful mission, Armstrong and Aldrin returned to the lunar module where Collins was waiting for them. Apollo 11 headed back to Earth, landing in the Pacific Ocean on July 24, 1969. Their return was a true triumph and was welcomed by millions of people around the world. The mission showed that humanity can achieve the impossible and inspired generations of scientists, engineers, and dreamers. The first moon landing inspired the scientific community to explore further. A lot of the technology developed for the mission became used in everyday life as well. It also had a huge impact on culture. Books, movies, and artwork of the time are steeped in the spirit of space discovery. The moon landing made people realize that the limits of what is possible lie only in our ability to dream and overcome obstacles. Don't forget to subscribe to our channel so you won't miss new interesting videos about space and the history of its exploration. Write your ideas in the comments. Maybe your idea will become the basis for our next video.
Silence filled with secrets. The night sky looks peaceful, a dome of stars, a glowing band of the Milky Way, distant galaxies painted like faint brushstrokes across the black canvas. To the human eye, it feels calm, a perfect silence, a sanctuary beyond Earth's noise. But this stillness is an illusion. Space is not empty, and it is not quiet. Every point of darkness hides movement. Every breath of silence is saturated with invisible radiation, drifting particles, and immense forces twisting space-time itself. To stand beneath the stars and feel safe is like standing at the edge of a stormy ocean, hearing no sound but knowing waves of unimaginable power roll beneath the surface. For thousands of years, humanity has gazed upward and found comfort in this illusion. Ancient cultures mapped constellations, told stories of gods and heroes, believing the heavens eternal and unchanging. Even in the scientific age, the universe often seemed like a stable backdrop, vast, indifferent, but constant. Now, that illusion is fading. The 21st century has given us a new observer, not human, not limited by tired eyes or slow thoughts. Quantum artificial intelligence. Unlike telescopes that merely collect light, unlike scientists who interpret data through human filters, this machine consumes oceans of information and finds patterns no mind could see. And what it finds is disturbing. Where we see stars glittering like jewels, it sees unstable furnaces on the brink of collapse. Where we see black velvet emptiness, it sees radiation, threats, predators moving silently through the void. The silence of the cosmos is not peace. It is camouflage. The question is, what happens when something finally learns to pierce the veil? The birth of a new cosmic observer. Astronomy has always advanced alongside technology. In 1609, Galileo lifted a small telescope and shattered the old view of a perfect heaven by finding moons circling Jupiter. In the 19th century, spectroscopy revealed that stars were not mystical fires, but suns burning hydrogen and helium. In the 20th century, radio telescopes uncovered pulsars, quasars, and the faint echo of the Big Bang itself. Each leap brought us closer to truth, but each also revealed a deeper mystery. The 21st century, however, presented a new challenge: too much information. Modern observatories from Hubble and James Webb to massive radio arrays like LOFAR and the Square Kilometre Array generate petabytes of data every year. Every star flicker, every gravitational lens, every pulse of radiation is recorded. But no human team can process it all. The universe has become a puzzle too vast for us to assemble. Quantum AI was built to solve this. Unlike classical algorithms, it doesn't just search for predefined patterns. It discovers. It compares billions of light curves, maps galactic rotations, and cross-checks gravitational anomalies with the precision of 1 million scientists working in unison. And it does so in moments. Already, it has achieved the impossible. Detecting exoplanets smaller than Earth by subtle variations in starlight. Mapping dark matter by analyzing gravitational lensing across thousands of galaxies. Predicting asteroid trajectories centuries ahead with near-perfect accuracy. Reconstructing incomplete cosmic signals, turning apparent noise into coherent structures. But with these victories came unease. When AI was fed NASA's newest Atlas images of deep space, it did not simply catalog stars and galaxies. It began flagging regions where something strange was happening. Places where radiation spikes aligned in ways no natural process could explain. Zones of gravitational distortion without visible mass. Streams of particles with no identifiable source. To human eyes, these were statistical errors, random fluctuations, or background noise. To the AI, they were patterns precise, repeat, undeniable. It was as if the universe had been speaking all along, and only now, through the cold eyes of a machine, had we begun to hear it. Rogue black holes, the invisible predators. While investigating gravitational anomalies, the AI uncovered signs of invisible mass moving through star fields, the telltale fingerprints of rogue black holes. These wanderers, flung from galactic collisions or supernova kicks, drift unseen across interstellar space. For years, astronomers assumed they were rare, but the AI suggests the opposite. The galaxy may be littered with them. Dozens, perhaps hundreds of rogue black holes within striking distance over cosmic timescales. The danger is subtle but immense. A rogue passing near our solar system could distort orbits, destabilize comets in the Oort cloud, and send a rain of icy missiles toward Earth. Closer still, it could strip Earth from the sun's embrace entirely, leaving our world a frozen orphan drifting in darkness. They are the ultimate predators, silent, invisible, unstoppable. Solar fury, a familiar threat reimagined. Even our own star is not safe. Solar flares and coronal mass ejection CMEs are familiar hazards, their beauty seen in auroras dancing across polar skies. But the AI detected long-term cycles in solar activity that defy current models. TS simulations predict storms far more powerful than the infamous Carrington event of 1859. Storms capable of crippling satellites, erasing power grids, and throwing our digital civilization into chaos. In a world where everything depends on fragile electronics, such an event could mean global paralysis. The unsettling truth: while we fear the distant void, one of the greatest threats to our survival may already burn above our heads. Cosmic rays, the invisible knives. You are being pierced right now, not by bullets, not by beams of light, but by cosmic rays. High-energy particles traveling close to the speed of light. They come from every direction, born in the most violent events the universe can produce. Most are harmless, stopped by Earth's atmosphere or deflected by its magnetic shield, but some penetrate, reaching the ground, even cutting through your body as you listen. A single proton, accelerated by a supernova millions of light years away, can strike DNA like a knife. For decades, cosmic rays were considered background noise, something scientists measured but rarely feared. Now, quantum AI tells a different story. By analyzing millions of particle detections, it discovered disturbing patterns. Streams of radiation that do not point to any known astrophysical source. Sudden bursts aligned with distant gamma-ray events, as though the cosmos itself fired volleys in coordinated rhythms. A subtle, but measurable increase in the flux of ultra-high energy particles striking Earth in recent decades. The implications are unsettling. For astronauts, cosmic rays are lethal companions. Long missions to Mars or beyond mean constant exposure. Cancer risk rises. DNA breaks. Nervous systems fail. On Earth, Airline crews flying at high altitudes already receive higher doses than those on the ground. But the AI's deeper fear is evolution itself. Cosmic rays, by shattering DNA, may have shaped the course of life on Earth. Extinctions, mutations, sudden evolutionary leaps all may carry the fingerprints of invisible visitors from the stars. What once seemed random is now mapped with eerie precision, and the message is clear. The universe is not a safe cradle. It is a battlefield of radiation, and we are fragile organisms, surviving only by chance. Cosmic rays showed us how fragile we are, but the next discovery is even more disturbing. Part 2. The Ghost Particles. Coming soon.
Saturn is one of the most mysterious and beautiful objects in our solar system. Its rings and many satellites make it unique and fascinating to study. In this text, we will delve into the mysteries of Saturn, its rings, composition, and amazing satellites. Saturn is a gas giant, the second largest planet in the solar system after Jupiter. Its diameter is about 120,000 kilometers, which is about 9 times the diameter of Earth. Saturn is mostly made up of hydrogen and helium, and its density is so low that if you could put it in a giant ocean, it would float. But Saturn's main calling card is its rings. They are so unique that Saturn is often referred to as the planet of the rings. Saturn's rings are a true cosmic masterpiece. They are made up of billions of particles of ice, rock, and dust that orbit around the planet. These particles can range in size from a speck of dust to huge icebergs. The rings look smooth and uniform from afar, but they are actually made up of many separate structures. Width and thickness. The main rings extend about 280,000 kilometers from Saturn, but they are only a few tens of meters thick. This incredible combination of scales is what makes Saturn's rings so impressive. Scientists are still arguing about how the rings came to be. They may have formed from the remnants of a collapsed satellite or comet caught in Saturn's gravitational field. Others believe that the rings appeared together with the planet. Although the rings appear to be uniformly colored, they are composed of several belts that vary in brightness and composition. These differences depend on the size of the particles and their chemical composition. Saturn's satellites. Saturn has more than 80 satellites, and each one is unique. Here are a few of the most amazing ones. Titan. Titan is Saturn's largest satellite and the second largest satellite in the solar system after Ganymede. It is covered in a thick atmosphere made up mostly of nitrogen and has lakes, rivers, and seas ... but of methane and ethane. The temperature on Titan is so low that the water there is in a solid state, and the liquid on the surface is hydrocarbons. Scientists believe there may be a hidden ocean under Titan's icy crust where life is possible. Enceladus. This small satellite is astonishingly active. Geysers constantly erupt from its surface, ejecting water, ice, and organic matter. Scientists believe that beneath Enceladus' icy shell is a global ocean heated by internal thermal processes. This ocean is one of the most promising places to look for life beyond Earth. Japet. Japet is famous for its strange contrasts. One half of its surface is as dark as coal, while the other half is bright and icy. The reasons for this phenomenon are still a mystery. Mimas. This satellite is often compared to the Death Star from Star Wars because of the huge Herschel crater that occupies most of its surface. Hyperion. Hyperion is a chaotically rotating satellite with an unusual, spongy surface. Its porous structure makes it unique among other objects in the solar system. Interesting facts about Saturn. A day on Saturn lasts only 10.5 hours. It is one of the fastest rotating planets in the solar system. Seasons on Saturn vary due to its tilted axis, and each season lasts about 7 Earth years. Magnetic field. Saturn has a powerful magnetic field that creates stunning auroras at its poles. Clouds. Saturn's upper atmosphere is covered with clouds that form bands similar to those seen on Jupiter. Sometimes giant storms appear on Saturn, visible even from Earth. Why is Saturn so important to science? Saturn and its satellites provide a unique laboratory for studying many processes in the solar system. Satellites like Titan and Enceladus can provide clues about how life may have arisen. Saturn's rings help scientists understand how the planets and satellites formed. The Cassini mission, which ended in 2017, provided a wealth of data about Saturn and its satellites. Thanks to it, we learned that Saturn is much more than just a beautiful planet with rings. It is a whole world of mysteries that are yet to be solved. Saturn is a true cosmic gem. Its rings are breathtaking in their beauty and scale, and its satellites offer scientists incredible opportunities for exploration. This planet reminds us how amazing our solar system is and how many more mysteries it holds. If you are interested in such exciting stories about planets and space, be sure to subscribe to the channel, give it a like, and share this video with your friends.
Black holes, the ultimate cosmic spinners. The hidden pulse of the universe. Have you ever wondered why everything spins? From the tiniest atom to the largest galaxy, everything in existence seems to dance, to rotate, to spiral endlessly. Even you, sitting and watching this video, are moving right now, spinning with the Earth, orbiting the Sun, carried through the Milky Way. Nothing in the universe stands still. But what if this motion isn't random? What if this eternal cosmic dance hides the most powerful secret of all? A force so strong it can twist space itself, bend time, and perhaps rewrite reality? Welcome to the story of black holes, the ultimate cosmic spinners. The hidden dance of the universe. The universe doesn't move in straight lines. It swirls, flows, and twists like a grand cosmic symphony. From spinning electrons and protons within atoms, to massive planets orbiting their suns, to galaxies rotating like luminous whirlpools in an ocean of stars, the pattern is universal. Scientists call it angular momentum, but philosophers might call it the breath of the cosmos. Rotation gives structure to everything we know. Without it, galaxies would collapse, planets wouldn't form, and even time itself might lose direction. Spin is not just motion, it's identity. An electron is its spin. A planet exists because of its rotation, and the universe is defined by its endless turning. But where does this movement come from? Why does everything from the smallest particle to the largest galaxy need to spin? Could the answer lie in the darkest places in the cosmos? Places where motion reaches its ultimate limit? When gravity starts to spin, gravity doesn't just pull, it twists. According to Einstein's theory of general relativity, every massive object bends the space around it. But if that object also rotates, it drags space along, like a spoon stirring thick cosmic honey. This effect is called frame dragging, and nowhere in the universe is it stronger than near a rotating black hole. Imagine space-time, the fabric of reality, being twisted and pulled into a whirlpool. Anything that gets too close is caught in the dance. Light bends, time slows, and beyond a certain point, nothing can escape. This is not just gravity anymore. This is cosmic spin at its most extreme, a place where motion becomes destiny. If spin can twist time itself, what happens to something or someone who falls into that spinning abyss? Would they see time reverse? Or would they become part of the eternal rotation of the universe? Birth of a black hole. Every story of creation begins with destruction. A black hole is not born quietly. It's the final scream of a dying star, a collapse so violent that the laws of physics themselves are torn apart. When a massive star runs out of fuel, its nuclear fire, the fragile balance against gravity, fades away. Gravity wins. The outer layers are thrown into space in a final blinding supernova. But the core, the heart, falls inward. It compresses and compresses and compresses until all matter becomes one single point, infinitely small, infinitely dense. In that instant, time and space lose meaning. The star is gone, and what remains is pure gravity, a bottomless pit hidden behind the veil of darkness. A black hole is born. Around it, the fabric of the universe quivers. The very geometry of reality bends inward, and with it, motion, energy, and time begin their eternal spin. If death can give birth to something so powerful, what does that say about the universe itself? Maybe every end is only the beginning of a deeper rotation. The accretion disk, the brightest darkness. When matter falls toward a black hole, it doesn't simply disappear. It orbits, it spirals, it dances faster and faster until friction and gravity set it on fire. This furious motion forms a glowing disk around the black hole, an accretion disk, and paradoxically, the region around the darkest object in existence becomes one of the brightest in the cosmos. Gas and dust stretch into thin streams of plasma, moving at nearly the speed of light. Temperatures soar to millions of degrees. Radiation floods across space, outshining entire galaxies. We call it the brightest darkness. What you see is not the black hole itself, but the energy of its spin, the light created by matter's desperate struggle against gravity. The closer it gets to the event horizon, the more it glows, before it vanishes forever. What you see is not the black hole itself, but the energy of its spin, the light created by matter's desperate struggle against gravity. The closer it gets to the event horizon, the more it glows, before it vanishes forever. To fall into a black hole is to fall into motion itself, a motion that never ends. And if everything that touches a black hole becomes part of its rotation, then maybe, somewhere inside, the memory of every star still spins endlessly. The spin that bends time. Now, imagine a place where time itself begins to twist, where the future and the past blur into one continuous motion. That's what happens around a rotating black hole. Scientists call it a Kerr black hole. Unlike a static one, it doesn't just bend light, it drags space-time with it. Everything nearby, matter, energy, even time, is pulled into rotation. This phenomenon is known as frame dragging. If you could hover near such a black hole and survive, you'd see time flow differently for every direction you move. Turn one way, and you move into the future faster. Turn the other, and you might slip into the past. It's not science fiction, it's pure Einstein. Inside this cosmic whirlpool, the universe reveals a haunting symmetry. The faster something spins, the more it bends reality. If we could control such rotation, if humanity ever mastered spin on this scale, could we bend time itself? Would we become travelers? Or prisoners of the same eternal loop that rules the stars? The fastest spinners in the universe. Not all black holes spin equally. Some rotate lazily, dragging the nearby space like a gentle tide, but others spin at nearly the speed of light. These are the Kerr black holes, the most extreme rotators in the universe. Their speed is so immense that they flatten space itself, stretching the event horizon into a perfect ring. Imagine an object so dense, so fast, that one full rotation could happen in mere milliseconds. The energy trapped in that spin is beyond imagination, enough to power entire galaxies for billions of years. From their poles, twin jets of light and radiation burst outward, piercing across thousands of light years. These jets, fueled by rotation, carve the structure of galaxies themselves. The universe, it seems, uses spin as its brush. Every spiral, every orbit, every galaxy, a trace of this invisible force painting reality. But how fast can something spin before the laws of physics say, enough? Some black holes dance so close to that edge that even time trembles, unsure if it should move forward or stop. Black holes versus neutron stars. Black holes are not the only masters of spin. Their smaller cousins, neutron stars, are cosmic gyroscopes that defy reason. A neutron star can spin hundreds of times per second. Some even reach thousands. Imagine a sphere the size of a city, heavier than the sun, spinning faster than a blender blade. Their magnetic fields are colossal, strong enough to rip atoms apart. They flash with every turn, sending rhythmic pulses of light across the galaxy. That's why we call them pulsars, cosmic beacons marking the rhythm of the universe. Next to a black hole, they seem fragile, but both are children of the same chaos. born from dying stars, defined by rotation. It's as if the universe can't decide which form of motion it prefers: the visible brilliance of a pulsar, or the silent, devouring spin of a black hole. Perhaps they are two sides of one truth. That motion is the ultimate language of existence. The spin mystery. Who gave the universe its twist? Every spin needs a beginning, but where did the first rotation come from? After the Big Bang, the newborn universe was a storm of energy, pure chaos. Yet somehow, out of that explosion, order emerged. Tiny fluctuations became patterns, and those patterns began to move, to rotate, to spin. Physicists call it angular momentum conservation, but maybe there's something deeper. Maybe the universe was born spinning, a single cosmic breath that set everything in motion, from electrons to galaxies. And if that's true, then motion isn't just a property of the universe. It is the universe. Every thought, every heartbeat, every orbit, every sunrise on every world, all of it echoes the same original twist that began 13.8 billion years ago. Maybe creation itself was not a bang, but a spin. The philosophical spin. Look long enough into space, and you realize the universe is not chaotic, it's choreographed. Every orbit is a rhythm, every star a dancer, every galaxy a movement in an infinite waltz. We are part of that dance. Our atoms once spun inside ancient stars, and one day their remnants will spin again, in some new form, in some new world. To spin is to exist. To rotate is to live. To stop is to disappear. Maybe consciousness itself is born from this same pattern, a self-aware echo of the cosmic rotation. We think, we move, we dream, all following the same curve that galaxies trace in silence. And as we look at the stars, we're not just watching them move, we're watching ourselves. The ultimate question. At the center of a spinning black hole, time ceases to behave. Space folds, reality curves inward. No one knows what lies beyond that boundary. Some physicists suggest it's a passage, a doorway to another universe, born from the rotation of this one. Others believe it's the ultimate dead end, where information, energy, even time itself are shredded beyond repair. But maybe both are true. Maybe the black hole isn't an end, but a bridge, a point where the universe folds into itself, and then begins again. What if the cosmos is not expanding in a straight line, but turning endlessly, like a spiral of existence? What if every Big Bang is just the other side of a black hole? Would that mean our universe is alive, beating, spinning, breathing in cycles without end? Look up, the stars are moving, the galaxies are turning, and so are we. The dance never ends, it only changes form. This is the spin of the universe. This is where darkness becomes motion. This is where everything begins again.